My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Center, and School of Astrophysics and Astronomy, and YouTube channel, Pretam Kumar Das, I would like to welcome you all to our International Physics webinar. A good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. Today, it's our 193rd International Physics webinar. So hope you are well and safe from corona pandemics. As we know that we are staying in a corona pandemic situation, and situations are becoming worse day by day. So we have to follow the health rule. It is very difficult for us to continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. We have successfully completed our 192nd International Physics webinar, including 2 Nobel laureate speakers. And today it's our 193rd International Physics webinar. And today I'd like to welcome you all to a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Department of Physics, College of Science, University of Texas at Arlington, USA. And we have with us here today Dr. Dora Elia Musielak, Madam, Research Professor, Department of Physics, College of Science, University of Texas at Arlington, USA. And she has already connected with us. So I'd like to welcome our speaker. Madam, good morning, Shubho Shakal. And good evening here, Shubho Sandhya. Thanks for accepting our invitation. It's my honor and privilege to host you in my International Physics webinar. So before going to you, I'd like to introduce you with our student and viewers. So dear viewers and students, I think you have already come to know the title of this today's International Physics webinar, and title is the Spacecraft Propulsion, Launch and Orbit Design, Rocket Scientists Give to Exoplanet Scientist. And our speaker is Dr. Dora Elia Musielak, Research Professor, Department of Physics, College of Science, University of Texas at Arlington, USA. So I would like to welcome our speaker again. So you can, dear student and viewers, you can also join with us by using this link, and you can also ask questions by commenting in Facebook and YouTube. So, Madam, I'd like to welcome you again. It's your time, Madam. You can start your session. And thanks for giving us this opportunity to announce this important and exciting webinar with you.
Masha. Thank you, Dr. Kumar Das. Shubha Sandhya. It is appreciate very much your invitation. It is quite an honor to be among all these renowned, very well-known physicists and astronomers that have joined your International Physics webinar. It is an outstanding idea on your part to bring together all these incredible individuals who are making the advances in physics and astronomy, astrophysics, to take us to the next level. And hopefully, my presentation serves also to inspire students to pursue a completely different area of research that, as I said here, this is from the perspective not from a physicist, not from an astronomer, but from a rocket scientist. Okay, so again, I wanted to be sure that I greet everybody. Shubha Sandhya. It is a great pleasure to be with you. Well, among the millions and millions of exoplanets that we believe are orbiting the millions and millions of stars in our universe, over 4,000 have been confirmed. But the most amazing thing is that those exoplanets, most of them have been detected through space observatories. And I put here a graphic to represent the different missions to do the detection and the research on these bodies that are all over our universe. So all the space observatories that are here obviously work in conjunction with ground-based observatories. And also some of these space telescopes were not intended for exoplanet research. In fact, the first dedicated space observatory to detect exoplanets was Korot from the Europeans. But then Americans came out with a Kepler mission that it really revolutionized, the detection of exoplanets. And of course, most of those exoplanets were detected by Kepler. And of course, there are still some missions ongoing, and some that will continue searching for a better understanding of exoplanet structure, the atmosphere, their moons, and of course, their habitability. But of course, my talk is not about the exoplanets per se. My talk is about where do these space telescopes must be located. That is, it's wonderful to talk about exoplanets, but as astronomers and physicists and astrophysicists must realize that there is another group of individuals worried about where do we put telescopes in order for them to continue searching for exoplanets. Here is a summary of the research done by these space telescopes. And so Hubble and Spitzer, of course, they were not meant to be exoplanet searchers, but they have contributed to our understanding of exoplanets. Korot, actually from the European, that was the pioneering spacecraft that really told us that it was possible to get the signals from these exoplanets. And of course, again, Kepler came along, and now we have TESS that is still in orbit, from the European, the CHOPS. And of course, we have a number of other missions that are coming very soon. But if we look at the right-hand side of this chart, here is a summary of the orbits that each one of these telescopes has to follow. And of course, the Hubble that has revolutionized astronomy in general, it orbits very close to us, just above our head, at a low orbit of about 540 kilometers above our head. And then, of course, Korot follow as sun-synchronous geocentric polar orbits, that is very, very well known. But then Kepler came and followed a completely different one, a heliocentric Earth-trailing orbit. And again, this helps us understand where they are located, and of course, where now astronomers feel that they need to put the new telescopes in order to fulfill the requirements. So I'm going to be talking more about orbits rather than the missions themselves. So let us start putting this into perspective, okay? In 2018, the SpaceX Falcon launcher sent TESS spacecraft into a supra-synchronous transfer orbit, about 200 kilometers above our head. And after, some maneuvers, this telescope was deployed into highly elliptical orbits. It was about 48 minutes after liftoff. And of course, for the rocket scientists, we're dealing with nonlinear equations of motion, very challenging mathematically, and of course, technologically extremely difficult. And of course, this is just the very beginning, the first step for us to send an exoplanet searching telescope into the correct orbit. But this is not the whole story, right? Most people see when the launch happens, but what happened to the spacecraft itself? Okay, after deployment, there was a lot more work that the rocket scientist group had to do in order to ensure that this precious cargo, this precious payload, which is the Space Telescope, arrived where it needed to be. And so if I were to give you a course on this topic, I will have to talk obviously about the exoplanet missions, about the requirements that exoplanet scientists have in order to put this telescope in orbit. But then I will have to go into rocket science, my area of expertise, okay? Optimizing the spacecraft launch, which is a lot of issues, and then ensuring that the space telescope stays in orbit in the correct position. This is a very precise play of mathematics, physics, astronomy, and of course technology. And of course, and then once that a payload, our space telescope is in orbit, then we want to keep it there. So we need to talk about orbital mechanics, the two-body problem, then the restricted three-body problem, which is another extreme complicated area of research for us, the rocket scientists. And of course, then we don't have time for all that. So let's just start by just summarizing some of the exoplanet discovery missions. TESS, Kepler, and Kepler already concluded its mission. And then what is coming, starting hopefully in October of this year, is the Webb Space Telescope, the successor to the Hubble. And this telescope is going to study the atmospheres of the known exoplanets. And of course, one of his goals is to find Jupiter-sized exoplanets with the tools that it will carry on board. And another mission that is coming, I suspect that later, is what we used to call the Wide Field Infrared Survey Telescope. Now it was renamed as the Nancy Grace Roman Space Telescope after a very well-known woman astronomer at NASA. But again, the question that people like me ask is, where do we put these telescopes in order to better study the exoplanets? This is not a trivial question. It's probably the most important, because this spacecraft, these telescopes, must be in a very precise place. So if I talk with an exoplanet scientist and talk about the orbit requirements, the ideal orbit for this mission would be to allow for continuous observation of the exoplanet, or the star where the exoplanet is orbiting, that must last for X amount of time. It can be days, weeks, etc. Be stable to perturbations over the mission duration time. And of course, it has to offer low radiation environment, offer stable thermal environment, and of course, achieve this orbit with a moderate change in velocity, because change in velocity represents power, energy, rockets that we need to put into the observatory in order to maintain its orbit. And so again, we have to talk about the type of orbits that we can really pursue. So, like I said, the Hubble is right here over our heads. We can say it's the lowest of the lowest. This is in a low Earth orbit. Well, we can also place an observatory on a high Earth orbit, and this is above the belts, and so it's far away from radiation from the belts. It is about up to 35,000 kilometers over our heads. So some of our missions have chosen high Earth orbits. And so, you know, there are reasons why these are good compared with lower orbits. And of course, but most importantly, I must say, is that the ideal orbit is specific to the mission. One example is Kepler. Kepler had as an objective to find Earth-sized planets in the habitable zone, okay? And that required continuous viewing of the star fields near the galactic plane. And so it had to be away from the moon. So after doing a number of analysis, researchers came up with the best orbit for Kepler was a heliocentric Earth-trailing orbit. And so you see, orbit requirements are specific to the mission. And so we cannot say which one is best. It is what is best for what our telescope needs to achieve. But there is one more thing, in addition to the orbit, is do we have the capability to put this space telescope from the perspective of the rocket scientist, the exoplanet spacecraft required to be launched by rocket propulsion to overcome, you know, Earth's gravitational field, and also to gain the huge speeds that is needed to orbit the central body. The central body can be Earth, you know, we can have a geocentric orbit, or the sun, or be in one of the so-called Lagrange equilibrium points. In addition, you know, the technology for space launchers, you know, has to be consistent with its capability to put this precious payload that has different mass into orbit. So, for example, let's say that TESS was launched by Falcon 5, but TESS was a tiny little space telescope, had a launch mass of only 362 kilograms. But to launch the Webb, this is a humongous space telescope that has a spacecraft launch mass of 6,200 kilograms. For that, we're going to need a completely different rocket launcher. And the Ariane from Europe is going to do the job. So again, you know, there's an optimization problem that first start with the launch of this space telescope. So getting a perspective on the telescope, on the launch, lifting a spacecraft to lower orbit, which, you know, about 300 kilometers, which is very low, requires energy. And yeah, we need huge rocket launch vehicles. But then staying in orbit requires even more energy, which means that our space telescopes have to have built-in thrusters for them to maintain orbit control, okay? And there's one more thing, you know, the launch system has to have the capability to put the size and volume of the vehicle. And so here, this is a pictorial, artistic pictorial representation of how the Webb is going to fit in the Ariane 5 nose from here it would be deployed. So anyway, that's the reason why my title is Rocket Scientist's Gift to Exoplanet Science, because without it, without rocket scientists, we cannot put this exoplanet telescopes in orbit. So again, there is a great range of work that needs to be done. I seem to lost them. We need to consider launch analysis, mission analysis, and this is a complex. Dr. Kumar, is my presentation being? Is it being displayed? I see that it.
Yeah. We can. Yeah. Okay. We can see.
Disappear from.
Yes.
So again, propulsion is not only required for launching the space telescope, but also it has to be built in. And so when we put this telescope design, it has to include the propulsion system, and of course the propulsion system requires propellant in order to do its job. And so, this is an example of Kepler that it ran out of gas eventually after doing a number of things that was carrying 12 kilograms of propellant in its fuel tank, and of course it ran out of gas. But anyway, my point is I'm just trying to express, how astronomers and physicists sometimes forget that there's a lot more than just detecting the exoplanet, which is a very complicated process. Okay, so now let's get into concept of orbit analysis. Again, we can design an orbit using the two-body problem. This involves closed orbits. We use this also for doing trajectory analysis, and then of course some other orbits requires us to use a restricted three-body problem, and so near Earth spacecraft orbits may be analyzed as a two-body problem or a restricted two-body problem. In the Sun-Earth-Moon system, we can come out with a large variety of unique orbits that are based on the restricted four-body problem. And remember, the restricted three-body problem or the two-body problem refer to the fact that, for example, if we have a spacecraft in low orbit, so this is a two-body problem. This is, we're just concerned about the interaction between the large body, which is the Earth, and the spacecraft. But if we go a little farther, then we have the interaction of the moon, the sun, etc. So, then we can no longer treat this problem as a two-body problem. And so we need to consider, the gravitational field of other astronomical bodies in the vicinity where the spacecraft is going to operate. Okay, again, I'm not going to give a class on two-body problems, but this is just a representation of the Keplerian motion. And all I wanted to indicate here is there's something important for us to understand, how the spacecraft is going to be in this particular orbit. And mostly important is the velocity at any point on the orbit, because it's going to tell us how much energy that spacecraft must consume and help us understand how much propellant we need to have in order for the spacecraft to do its job. Another very important aspect of this analysis and understanding the sphere of influence. For those of you astronomers, well, everybody, we know that near a given planet, the influence of its own gravity exceeds that of the sun. The Earth's surface gravitation force is over 1,600 times greater than the sun's, right? So within a planet's sphere of influence, the spacecraft motion is determined by its equation of motion relative to the planet. But like I said, if this orbit is going to be outside, then the spacecraft has to get out of the sphere of influence of the body. Obviously, every body in this radius of influence, here's a comparison between the moons and the Earth. So this is important for us to know where we're going to put the spacecraft. We need to know the types of orbits that they are, elliptical, parabolic, hyperbolic. We need to understand the escape velocity from a given astronomical body, and that is going to tell us the level of hyperbolic excess velocity that is required for the spacecraft to exit the sphere of us. And another important thing, like I said, the spacecraft velocity is predetermined, and but then it has to make little adjustments along the way. So we need to know what those velocity changes, and that's what we call the delta V, is going to require for maneuvering in space in order to do and stay within the orbit parameters that we have predetermined for it. I put an example here just to illustrate, a spacecraft with initial circular LEO altitude, let's say 300 kilometers, must transfer to elliptic orbit with 300 kilometers altitude at perigee and 3,000 kilometers at apogee. So we need to determine what is the velocity increase, what is the delta V, okay? And so we find that it requires about less than 1 kilometer per second. This has to be done by external propulsion, okay? And so we do this obviously for more complicated scenarios in the exoplanet search missions. Very, very important also is the minimal energy trajectory. So, like for example, let's say we're going to the moon. What effect the injection speed, is given by the launch vehicle, has in attaining lunar orbit. So if we assume that the orbit injection into lunar trajectory occurs at the perigee with zero inclination, so we know that to reach that lunar orbit from, let's say, a parking orbit of 320 kilometers, which is typical, here on near the Earth, the spacecraft requires an injection speed of about 10.8 kilometers per second. So this is important for us to know whether our launch rockets have the capability to put our exoplanet detecting or research telescope is going to reach its destination. And so this is a very, very important case. And the limiting is that injection speed, which is infinite. This is a path that is straight line with a time of flight zero. So this is an example just to put this in perspectives. Ariane 5, these are performance estimates for this launch system. If we were going to use Ariane to send a space telescope on a moon orbit, for example, it will have to reach Earth escape. It can handle up to 4,500 kilograms payload. If it's an escape orbit, these are the capability that this launch system has. And of course, all this data for each launch system that exists in the world, it is important for us. So when we do the analysis as to our mission requirements are, which is to accommodate our payload, okay? Now, extremely important is the so-called launch characteristic energy. In our field, we call it the C3. This is a measure of excess specific energy over the required to just barely escape from a massive body. For example, we're always going to want to escape the Earth, but we could have a mission, that starts at the moon, so we want to, have escaping from the moon and so forth. And so here, the C3 launch characteristic energy is represented by this velocity at infinitive. And so this is a velocity at great distance from the planet, where the gravitational attraction is negligible, okay? So this velocity is attained when the spacecraft has climbed away from the departure planet following a given injection velocity. And again, you know, this is unique for the launch system, you know, the capability this has in order for us to achieve what we need for the mission. And this is just some more examples, you know, that I put here that I typically give to students for them to understand. For example, for the Kepler telescope, at the target intersect point, we knew that the perigee radius was about 6,500 kilometers. And the requirement for the C3 energy magnitude was on the order of 0.6 kilometers square per second square. And so that told us, you know, whether the launch, in this case, was a Delta II launch system from the US. So this rocket was able to put Kepler into a circular orbit, which is, it was the parking orbit before, you know, after coasting for about 43 minutes, then it reached the proper position to begin the second Earth departure sequence. And so it required, you know, another stage of the launch rocket that took about 90 seconds to burn. So it was about 2,000 kilograms of propellant in order to give us the propulsion required. So eventually Kepler separated and escaped to its heliocentric Earth trailing orbit, which, you know, this is amazing. And in fact, heliocentric Earth trailing orbit is absolutely great for exoplanet missions, you know, because it has, it's away from blockage from the Earth, from the sun. And so, you know, exoplanet research is done very well in this kind of Earth trailing orbit. It's a heliocentric orbit. Okay, so again, this is just some data from the Kepler. If you recall, it was launched in 2009, was on a 3.5-year mission. It was looking for Earth-like planets. It's one of the most successful missions ever, okay? It has discovered most of the exoplanets. Exoplanet scientists, I'm sure, can give you a better explanation than I can about the type of method it uses to determine the size of the exoplanet. And here, this is just some data that from a paper. I forgot to put the reference. But this is just a representation of the transit photometric method that is used by Kepler. So it uses this transits in front of the parent star. So it observes the brightness of the star, so it drops when the planet goes in front, and that helps determine the relative size of the star and the planet itself. So here is a pictorial representation of Kepler on its Earth trailing orbit. And there's a nice YouTube video that shows, you know, this sequence. Okay. So here's, you know, again, Earth trailing heliocentric orbits are absolutely wonderful for exoplanet research. And so as the name implies, the telescope trails behind the Earth. So it is at about 1 astronomical unit from the sun. So it is just trailing behind the Earth. So it doesn't have, you know, the Earth is not blocking its view. Okay. TESS, again, has a completely different orbit because it has other requirements. Remember, TESS has 4 identical cameras to survey the entire celestial sphere in 4-week increments. And so here it requires for it to be in a lunar resonant orbit. Okay, so what we say is that the spacecraft, the telescope, is in a 2-to-1 resonance with the moon. It makes about 2 revolutions around the Earth, and the moon makes 1. That's what it means by 2-to-1 resonance. So every time that there is perturbation to the orbit, it is corrected by the attraction of the moon. Okay, so the lunar resonant orbit is a heliocentric orbit. Provides long view periods without station keeping. In other words, it doesn't have to have a rocket to adjust the orbit periodically. So this is another, an orbit that was designed specifically for TESS, okay, because of these requirements. So let me move away from that. Here, it's much better than I make it, okay? Exoplanet scientists will appreciate, what rocket scientists call the cosmic dance for TESS. The way it happened, after launch insertion, TESS made 3.5 phase-in loops to raise the apogee to the lunar distance, okay? Then had a lunar flyby to increase the perigee radius and the inclination to the desired values that were calculated, beforehand. The gravitational assistant from the moon changed the orbit inclination to 37 degrees from the ecliptic plane. And finally, TESS performed large transfer orbits with a final maneuver to establish that 2-to-1 resonance that I talk about. So TESS had to use his propulsion to make those corrections to achieve the final orbit. So again, as you can see here, there's orbital mechanics, rocket science together in order to accomplish this, what we call TESS orbit trajectory cosmic dance, in order to arrive where it needed to be. Okay, there's a very nice paper of Parker et al. That describes, the design of this beautiful, beautiful, beautiful moon resonant orbit. And here, this is just to give you a perspective, also from the same paper by Parker. TESS executed a 2-month commissioning phase to put the spacecraft in its target mission orbit. And this was using small propulsion system, okay, with a change velocity of about 3 kilometers per second. And that was helped by gravity assist from the moon, okay? And so the stable resonance in this restricted 3-body problem refers to the tendency of a closed orbit to exhibit long-term stability without station-keeping maneuvers. Station-keeping means having little rockets to adjust the orbits, when its period is a ratio of that of perturbing body and proper phasing is established. This is called the Kosai-Lidov Mechanism. Some people call it Ledidov-Kosai mechanism. Either way, those two individuals deserve the name that goes along with that. Just to review very quickly, the Kosai-Lidov mechanism describes long-term behavior of a highly eccentric, highly inclined orbit subject to a third-body perturbation force. And so here in this lunar push, that was like in this case the moon, the perturbing body also helped to establish this dynamical phenomenon that was essential, for designing the TESS orbit. Okay. So now we move. I know that I cannot be here too long, even though I would love to talk forever. But future missions, starting with the Webb telescope, are planning to put the spacecraft in one of the Euler-Lagrange equilibrium points. Let's just review very quickly. Equilibrium points, those are regions near two large bodies, such as Sun and Earth, Moon, right? In orbit, where a smaller object, let's say a spacecraft, will maintain its position relative to a large orbiting bodies. At these positions, the combined gravitational pull of two large bodies provides precise centrifugal force required for the small body to rotate with them. So these Euler-Lagrange points that exist, like I say, wherever there are two large bodies, you want one in stable position with respect to those two big bodies. I call it the Euler-Lagrange points. They provide very stable thermal environment, which is required for detecting exoplanets, and that's the reason why the future missions are considering to put those space telescopes there. This is just my representation of those equilibrium points. And as shown here, I have equilibrium points in the Sun, Earth, Moon system. So we can take, like I said, just the points between the Sun and the Moon, or between the Earth, or between the Earth and the Moon, or we can just put them all together as I did here. So that gives it the reference frame. So what I call this Sun Earth L1 point is suited for making observations of the Sun Earth system. As EL2 is a great spot for space-based observatories. It has many great things, many characteristics that allow us to do that. And so that's the reason why it's chosen for future exoplanet missions. Now, I'm not going to go through this. This is just a description of the restricted three-body problem that, from work that I did, but I'm going to skip this. And I took this from Wikipedia. It tries to represent the spacecraft on the green spots, if you can recognize those green spots, at the Euler-Lagrange points, which are in equilibrium. It says, theoretically, at any other point, gravitational forces are not in equilibrium. In practice, however, orbits around L1, L2, and L3 are dynamically unstable, which means we need to put something there because small departures from equilibrium grow over time. So whatever telescope we put in L1, L2, or L3, eventually they're going to get out of their orbit. So we need to put little rockets, to push them back to where they need to be. So what I say here, spacecraft at these Lagrange points require propulsion to keep them where they need to be. There are two types of orbits that we can use for the SEL2 point. One is the Lissajous orbit. This is a quasi-periodic orbital trajectory that an object can follow around that point. Or we can use a hollow orbit. This is a periodic three-dimensional orbit that results from the interaction between the gravitational pull of the two primary bodies and the Coriolis and centrifugal accelerations on the spacecraft. Okay, so since 1978, I've been placed in orbit about L1 and L2 on the Sun, Earth, and Earth-Moon systems. Okay, so we have already experienced positioning a telescope there. And this is a pictorial representation of a halo orbit around L2 on the Earth-Moon system. Okay, so again, this goes back to the 90s, actually before the 90s, I'm sorry, 1970s, where all this analysis began. So we began to study, well, not me, because I was not yet a PhD, but transfer trajectories, considering different launch system, different orbits. And of course, a lot has changed in the past since the first analysis was done to transfer spacecraft into an L2 point. So since I'm running out of time, let me just quickly move into the James Webb Space Telescope, that it is hopefully to be launched in October of this year. This is, like we said, this is the successor to the Hubble. This is a huge system, and it's going to orbit on this rotation. So the distance between the L2 and the Earth is about 1.5 million kilometers. Remember, the Hubble is right here, very close to us. The Webb is going to be far away from us. This is just a pictorial of the launch and deployment. After launch, the Webb is going to travel about a month to reach its orbit to the SEL2 point, which is the second Euler-Lagrange point. And during that period of time that is moving to its destination, it's going to deploy its solar arrays. It's going to do a number of things in order to achieve, the full glory of what it's intended to do. Here's from a study done on the orbit. It says the Webb is at a point, which is about 4 times the Earth-Moon distance, by the way. Okay, and the orbit is about 6 months. Cell is a saddle point. In other words, as we say, it's not stable, and so it requires station keeping every 21 days. The telescope will fire onboard rockets to maintain the orbit. Okay, but this is some of the analysis that was done to do that. Now, I want to also point out one thing, that every time, and I'm involved right now in doing another mission, looking for the perfect orbit for the mission. We have to look at the comparison of the C3 and delta B for each possibility, and this is just using an example that was done back in 1993 for the Spitzer. It requires an escape orbit that does not require station keeping or minimum, and stay near the Earth to minimize communication requirements. The researchers at the time simulated an escape orbit with slightly varying energy and direction to determine the distance at the end of the 5 year that was originally established for Spitzer. And so they find that the orbit had an escape energy of 0.4 kilometers square over second square, compared with a high Earth orbit that required 2 maneuvers to achieve, resulting in an energy that was an order of magnitude greater, and the L2 point requires a minus. So this is the type of comparison that is done for every mission to see what is the best, depending on what we have and where you need to go. The one we used to call the Wide Field Infrared Survey Telescope, that now is called the Nancy Grace Telescope, Roman, is going to be launched in 2025, and and this will also say point where Webb is going to be. Let me skip that. This is from a paper in 2018, establishing the trajectory. And I'm going to conclude. I know that I have taken more time than I was supposed to, but I'm just going to tell you about this. It's a very futuristic in the sense that we're looking at the possibility of putting a spacecraft on the moon far side. And this is my representation of such orbit. So here, as you can see here, this is the Earth, the moon. The distance between them is written here. And the orbits would be on the Earth-Moon L2 point. It can be a hollow orbit like the one I represented here. Now, I should tell you that this is not new. In fact, the Chinese already have not a exoplanet search vehicle, but actually just a surveyor of the moon. It is already orbiting here with the hope of them placing a lander on the far side to be. But anyway, we're considering this for exoplanet research, so that it's possible for future studies. Okay, so I'm just going to mention the Dark Ages experiment that is going to is considered for the future. Now, for those of you who are interested, orbit design is extremely complex. The analysis for doing such is absolutely incredible. It requires powerful, some of the ones that are available to do spacecraft orbit design. And all of them, I put the links here for anybody who is interested. Again, I just want to say optimization process, it requires to minimize the necessary delta V to inject, the space probe from the launch vehicle park in orbit into the escape orbit that it needs for optimization. So, and for that, I'm just going to end this conversation with my message to students, because I did this for them. When Dr. Kumar Das issued the invitation and he mentioned that this is for inspiring students, I'm like, I'm on board, Professor. I'm with you, because really, this is extremely important. I love students because they are coming with new ideas. But let me just read to you what I wrote here. My message to students: space exploration and exoplanet research presents many challenging problems, 3-body problems, 4-body problems, etc., that rocket scientists and engineers help to resolve. So in other words, we're here with physicists, astronomers, exoplanet researchers, but many problems remain. We need to understand the motion of as yet to be designed space telescopes, solve the motion of interplanetary probes that can interact with planetary bodies, and determine spacecraft orbital maneuvers for missions to the moon, across the solar system, and beyond. Okay? All that and much more requires highly sophisticated analytical tools and new interdisciplinary research efforts by all of us. Please join me. Let's uncover the secrets of the heavens. And with that, I'm very happy if you join in, and hopefully this topic gives you some inspiration and ideas for your future career. Namaste.
Thank you. Thank you, madam, for your wonderful and exciting talk. And I think students and viewers have enjoyed it, as this is very interesting topic. So we have got few questions in inbox. So if you allow, I can start our discussion session. The first question. So what is the dark age?
Let's go here. Dark age radio experiments. It's a mission to study the universe 80 to 420 million years after birth. This is a mission. Let me go back a little bit here. This is a mission that is proposed to study the cosmic dark ages. Okay. The telescope for this mission requires quiet radio conditions that is shielded from the sun and the earth electromagnetic emissions. Okay. And this zone is only available on the lunar far side. That's the reason why that position right now is of great interest, not only for exoplanets, but also for this kind of studies, okay? Again, this is a proposed experiment. I should, I had to cut a lot of information here, but the person who's asking me, I'll be happy to provide a reference for this proposed mission, okay? But again, for this, the best position for such a space telescope would be on that side of the moon.
Okay, madam. So thank you. We have another question. So what is the escape orbit?
Oh, a very good question. And in fact, this is what makes. Remember, if we have let's say Hubble is orbiting in the sphere of influence of the Earth, okay, and so let me go back here to here, okay. So in order for us to leave the sphere of influence, we're going to have a launch system that take us from, let's say, the so-called injection point, which is a parking orbit. And it has to have enough energy, that velocity, to escape. And so we have the infinite velocity. This is a theoretical velocity attained when the spacecraft climbs away from the departure plane following this injection velocity. So here, this we call it the infinite velocity, depends on this injection velocity that is going to be given by the launch system itself, by the rockets, okay? And so not all launch systems have that capability. So for example, when we launch TESS, like I said, first two rockets burned and put it in that parking orbit, and then it requires a third stage for the rocket in order to give it that final injection velocity to take it, to go farther, closer to the moon. Remember, in order for the moon to help it, achieve this resonant orbit that we needed. So here is sort of like a definition of what that is. So if a launch system has an injection velocity, for example, of 11 kilometers per second, then you can calculate what is this escape velocity in order to go to where it needs to be, away from the Earth.
Thank you, madam. This may be the last question. So what is the delta V?
Yeah, delta V is a change in velocity. So for example, let's say you launch the telescope let's say to a low orbit, and it requires a certain velocity from 0 to, let's say, orbital velocity. But then you want to change from that, let's say that this is a very circular orbit, but you want to change the perigee. So you need to calculate how much velocity change you need from that velocity that it has, let's say 7.5 kilometers per second. But now to raise the perigee, you need, let's say, 0.5 kilometers per second. So you're going to have to add that with a propulsion system. So that is the change in velocity. And so for every mission, we need to determine those delta B's that are required either for adjusting the orbit or for moving from one orbit to another, let's say from a parking orbit to another orbit, from a heliocentric to from a geocentric to a heliocentric and so forth. So those changes in velocity, and that had to be done either by rockets or a combination of rockets and the influence of another body such as the moon.
Thank you, madam, for your wonderful presentation and exciting discussion session. So as our aim is to motivate and encourage our students in this corona pandemic situation, so thanks again for helping us in doing this important and important webinar. So I think students have learned a lot of things about this spacecraft propulsion method and exoplanet type things. And I think some of our students may fall in love in this research. So one more question from me. So if anybody from our part, from Bangladesh or my university want to join your research group, what he or she need to do, as we don't have any big satellite, big telescope. So can anybody join your group remotely, or can they work from far from your lab?
Well, at my university, there's a research group that is studying exoplanets, the exoplanet aspect. They don't know anything about propulsion, launch, and orbit design. Okay, they're basically interested in working with ground telescopes, getting the data, and coming out, with understanding of exoplanets. So there's that type of research, dedicated exclusively to exoplanets. Now, the aspect that I'm talking about, again, is done once a mission is established, or let's say NASA, the European Space Agency, another agency decides that they want to have a mission to do exoplanet research. And so they can establish, what the goals are. And if they are going to fund such activity, they can begin. Now, again, this, I hope I made it very clear, these are international teams. Like
yes.
TESS require a US launch system, but Webb require a European launch system. And so, you see, the capability from all the nations is required. It's not only about the technology, the infrastructure, but also about the researchers themselves. And so students who are interested in these topics, first, they need to join a group, whichever that is, wherever they are, and engage in that particular aspect of the work. Like here at my university, like I say, the group is studying just exoplanets. But that doesn't mean that there will not be funding to expand that, to do what I say that I am doing, which is to look into other positions in space for exoplanet telescopes. So the future is there. Students never give up. Always reach out to those who are doing it, and express your interest to join in.
Okay, madam. So thank you for your inspiration. So hopefully it will be helpful for our students and the viewers. So thanks again for helping us in arranging this webinar, and we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, madam. It's my honor and privilege to host you in my International Physics webinar. So bye for today, and hopefully in near future we can arrange another webinar with you.
So, I would love to come to Bangladesh. Yeah. Okay, bye.
Of course, I'll definitely invite you after the COVID for face-to-face session.
Okay. Thank you so much. Good luck to everybody. Good wishes.
Yeah.
Good night.
Bye.